Okay, welcome to the last video, 5D in Chapter 5 on probability. And this is going to be a little bit more of a theoretical video. I'm going to talk some about the Bayesian definition of probability and hopefully give you some insight into how we talk about confidence intervals, which is certainly one of the more confusing aspects of this course, how to precisely talk about confidence intervals. Um, so it's strange but true that there are multiple definitions of probability that are in use in statistics. In this class, we're going to use the frequentist definition. That's the one we've already emphasized. The probability of an event is the proportion of times that the event would occur if we could repeat the trial effectively an infinite number of times. So it's a relative frequency going from 0 to 1, as we've discussed in the previous three videos. But in Bayesian statistics, probability can also be used to quantify the degree of belief in something, in whether that could be whether an event happens or whether a particular statement is true. So 0 for it's impossible and 100% or 1 for you're certain that it's true. And in the case of random trials, these definitions are concordant, and that's why you can have multiple definitions in statistics and not cause a lot of problems. Because if you're thinking about something like flipping a coin, the flip of the coin can be either heads or tails. If it's a fair coin, they'd be equally likely. There's two possibilities, so you'd say the probability is 1/2. So our expectation of the number of heads and tails on a large number of trials is that they'll be equally frequent, and so that's the frequentist definition of probability, and it's 1/2. But also, if I flipped a coin once and covered it up so I couldn't see whether it was heads or tails, and I made a probability statement, a Bayesian probability statement about whether that particular coin was heads or tails, well, that's not talking about a repeated trial anymore. But still, I have equal uncertainty, and both options seem equally likely. And so a Bayesian would say it's fair to say that you can say there's a 50% chance or a probability of 0.5 that the coin is heads up or tails up before you see it. So we see that there's not really strong conflict between these definitions. Bayesians just use probability in an extended form in contexts that frequentists wouldn't. So the Bayesian definition can be applied to unique events like that coin flip I just talked about, but you can also make probability statements about parameters in a Bayesian setting. So once again, we're not going to do this a lot in this class. I'm just trying to discuss this other perspective on probability because I hope it'll help you understand something about confidence intervals. There's a longer discussion about how it's appropriate to use probability in this Bayesian context in this book by Edwin James, Probability Theory, The Logic of Science. It's fairly mathematical, but also fairly accessible as well. If you're interested in that, you can check it out, but that's certainly not required reading for this course. Okay, so remember that if we have a 95% confidence interval for something, say the mass of some organism, and let's say we have some real data and we say that our 95% confidence interval for the mass is going from 12.1 grams up to 14.5 grams. Remember that what we're supposed to say is that we're 95% confident that mu, the true parameter value, is between the bounds of that confidence intervals. I should have put grams on here, but you get the point, hopefully. We're not supposed to say, and we do not say, there's a 95% probability that mu is in that interval. We say we're 95% confident that mu is in that interval. And it's a very confusing thing that we have this particular jargon for it. So the frequentist explanation, and one we've already seen in this course, is that 12.1 grams and the population parameter mu and 14.5 grams, those are all constant values. Remember, the population parameter is the mu if you had the entire population, so there's no variability there. There's no sampling error there. It's the true value of the mean of the entire population by definition. So whatever value it is, it's a constant. And since there's no repeated trials when you're talking about three constants, it doesn't make sense to use probability in that context. So there's sort of a semantic argument that by definition we can't say this because it's not a context in which we should be using probability. And that's a reasonable explanation. But there's also a little bit of something odd going on there, because you'll remember that we talk about, well, if you did 100 experiments, you'd expect the truth to be in the confidence interval 95% of the time. So when you're thinking about experiments happening repeatedly, then it does seem like there's some use of probability in that context. And so it seems like this explanation, while valid, is a little bit of sidestepping some of the complexity here. So I want to walk through an example which I think is the clearest explanation for why a confidence interval is not a probability statement about the true parameter. And this is taken from this paper by Jesus Bayari and James Berger in 2004 in Statistical Science. If you want to read about it more thoroughly, you can look at that, but once again, that's not a required reading. Okay, so it's kind of a silly example, but it works out nicely. So it's not realistic, but it's kind of fun to think about. So let's imagine we have a machine that counts jelly beans, but it doesn't do a good job. It does it poorly. 50% of the time, it reports one more than the true number, and 50% of the time, it reports one less than the true number. So it's always off by one. But each of the counts is independent, so we're going to make those errors too big or too small independently each time. And let's say that you have time, an inclination to count the jar of jelly beans twice, but you don't want to spend enough time to do it 50 times or something. So you're just going to get two counts. A statistician says, you can make some X% confidence statement. If you measure twice and then you just say you can be X% confident that the true value is 1 plus the lowest count. So the idea is that you can add 1 to the lowest count, and that'll recover for the fact that sometimes if you underestimate things, you're off by 1 as an underestimate, so just adding 1 should account for that. Okay, so let's, once again, since we're talking about probabilities, let's think about some notation that we can use to discuss this in a clear manner. Let's say theta is the true count, and our two that's the true number, excuse me, and our two counts that we make with the machine are C sub 1 and C sub 2, so that's our data, and the statistician's saying we're going to use 1 plus the smaller of the two, so I'm just writing that as, we'll just call that value R, that's our final estimate, 1 plus the minimum of C1 and C2. All right, so let's think probabilistically based on this model. What do we know about these outcomes? The probability that the first count is 1 smaller than the true value, or that it's 1 larger, and same for the second count. Well, the problem states pretty explicitly that each of the counts is 0.5 probability of being too high or too low, and that these are independent, so the same things apply on the next roll. It doesn't matter what happened on the first roll, so we don't need to think about conditional probability or anything like that. So that's what the model tells us is going on. What does that say about this method that the statistician is proposing for us? So what's the probability that that method gives the correct answer, that it gives exactly theta versus, it could be 2 off. If both of our counts are overestimates and then we add 1 to that, then we're going to be 2 off from the true values. And how often does this happen? So you might want to pause here and think about the outcomes here and what the answers to these questions are. So given this setup, what are the probability that we get the answer right with this method, or that we're off by 2? Okay, so I'm going to go on. The probability that we get that our estimator gives the true value of theta is, it's going to work adding 1 to the smaller count if we get if the first count is theta minus 1 or the second count is theta minus 1. So if either one of our counts is an underestimate, then adding 1 to the smallest count should correct for that, and our estimate should work. So that's how the method works. We're going to be off by 2 if both of the counts are overestimates, both C1 and C2. Okay, hopefully that makes sense. So that's an and statement, and this is an or statement. So we can think about our rules of probability about how we calculate each of those things. So the probability that we get it right, it's that or statement. So these are not mutually exclusive, right? We could be underestimating on both of the counts. So we need to say, what's the probability that we're an underestimate on the first count, plus the probability we're an underestimate on the second count, minus the probability that both of them are underestimates. And remember, we subtract that joint probability because we don't want to double count that part of the outcome space. So that's 0.5 plus 0.5 minus the joint probability. Since they're independent, it should be just the product of 0.5 and 0.5, so that's 1/4. That's where that's coming from. So overall, 75% of the time, this method the statistician is telling us to use should work. And the other probability, the probability that it's off by 2, that's an and statement. And these are independent, so we can just multiply them. So 1/2 times 1/2 is 1/4. And pleasingly, these add up to 1, as they should, because those are the only two options. We're either going to get the estimate correct, or it's going to be off by 2 using this procedure. Okay, so hopefully you're all still with me. I know it's kind of a funky example, but we're about to have some insight here. Let's think about another way to calculate these numbers. If you'd prefer a graphical approach, you can think about, well, we can think about the count 1 being in the columns. You could be an underestimate or an overestimate, and then the count 2 will be the rows. You could be an underestimate or an overestimate there, and we were given 0.5 here. And because we were told it's independent, we can fill in all these joint probabilities by the products of the probabilities for the rows and the probabilities for the columns, right? So we have a 25% chance that they're both underestimates, 25% chance that the first one's an overestimate and the second one's an underestimate, etc. And just to highlight the places in which the statistician's procedure works, if either count 1 or count 2 is an underestimate, then taking the smaller count and adding 1 should correct for that problem. And so either of those situations should work. And so those are the 0.75 probability that we get the right answer from this procedure. And the other one is the 0.25 probability that we get it wrong. Okay, so that's the graphical sort of view of what's going on here. All right, and so what the statistician would have said to us is use this procedure and you can make a 75% confidence statement. It's not an interval because it's just 1 point on the number line, but the statistician, she's saying measure it twice and then you can be 75% confident that the true value is 1 plus the lowest count. Okay, and hopefully you can see that that is a true and precise procedure that we're being proposed here. It actually is 75% of the time this procedure should work. So that's why it's justified to call it a 75% confidence statement. But let's imagine we have some actual data. Let's imagine you do 2 counts and you get 543 on the first count and you get 545 on the second count. The minimum of those two is 543. If you add 1 to the minimum, the statistician's procedure gives you an estimate of 544. So the procedure says you're allowed to say you are 75% confident that there are 544 jelly beans in the jar. Okay, and that's fine and that's correct, but it's a little puzzling too. What's the probability that the truth is 544, given that this is the data? Assuming that everything about the model that we've been given is correct. I haven't lied to you about how the machine works. What is that probability? It seems like that probability should be 1, because there's no other possible value that could give you both of these if the counts are always guaranteed to be off by 1, right? 544 is right in the middle there, so that means the first one's an underestimate and the next one's an overestimate, and there's no other way to explain that data. Since that's the only possibility, it seems that it's guaranteed to be 544 is the true number, so it seems like it should have a probability of 1. And that is indeed the Bayesian probability of that parameter value. So we can see that the confidence statement and the probability that the truth has that exact value are not the same thing. The confidence statement is 75% confident, and the probability in this case is 1, right? So there's a difference there. Of course, the 2 counts differ only half the time, right? The first one can be an overestimate and the second one can be an underestimate. That's this situation. Or the first one could be an underestimate and the second one can be an overestimate. That's that situation. 50% of the time, the two differ from each other, and you have a situation like this where your 2 data points differ. And using a probability approach, you should be absolutely certain about what the true value is. The other 50% of the time, you get 2 counts that are the same. So let's say you do another jar, and you get 687 on both of the counts. The minimum of those is still 687, so your estimate, after you add 1, is 688. The confidence procedure still says you're 75% confident that the true count is 688. But now, if you think about the other perspective where we try to make a probability statement about the truth, what is the probability that the true value is 688, given that the data is 687 and 687? Now, this one's a little harder to think about. It sort of intuitively feels that since you're just as likely to underestimate as overestimate, that you should have the same probability for 688 as you do for 686. Those are both compatible with seeing 687 twice. They seem equally compatible. And those are the only two values that are compatible, so it should be somewhere around 0.5. But that's not really using the laws of probability. That's just sort of an intuition about how things are supposed to behave. If we have a conditional probability like this, where we have a probability of a true statement based on given a data set, conditional on that data set, we're supposed to use something like Bayes' rule, right? That tells us how to calculate conditional probabilities. So we could set that up as what's the probability of 688 given that data, and this is how it unpacks, replacing Bayes' rule with all of these pieces. The numerator, we can start to get parts of this. What's the probability if the truth were 688? What's the probability we'd get 687 on both counts? Well, we have to underestimate twice in a row, so it's 1/2 times 1/2. So that part's 1/4. But then we come to the next portion of this that we need to solve, and there we're making a probability statement about the true value of the parameter before we've looked at the data. And that's a Bayesian probability. We can tell it's a Bayesian probability because it's making some kind of statement about a parameter value that's not conditional on the data, so it's before you've seen the data. And it's really tricky to specify these things. These are called prior probabilities in Bayesian statistics. You don't need to worry about it because we're not going to do this in the class. We're not going to do this kind of Bayesian probability moving forward. But the point is, in order to do this problem correctly, you actually have to be able to make some statements about this that are not things that we have to, not statements that we have to make at all when we're using frequentist probability. So this intuition that these are 0.5 is really just an intuition. We'd actually have to have some extra information in order to solve it. So, but once again, it's probably not 75%. So once again, the confidence interval does not equal the Bayesian probability. So this, I realize this is an abstract example, but the important thing to realize is that these confidence procedures are making statements about repeated trials. If you conducted the experiment many, many times, you're confident in the procedure itself. You know that this procedure will work 75% of the time. It's not talking about after you've actually seen the data. And so that's why when we see the data and we make a confidence interval, we're not making a probability statement about the truth being in that interval. Instead, we're saying we're using a 95% confidence interval or a 75% confidence statement in this case. And that's a confidence statement about how often the procedure itself works. Okay, it's a subtle point. If this video confused you more than it helps, I would advise you to not worry about it. We're not going to be tested in detail on this video or the content of it. I just think in my experience in teaching this class, this example helps a lot of people think about why we use the term confidence rather than probability in this context of confidence intervals. So hopefully that helped, folks, and if not, feel free to ask us questions in lecture, and most of the problems that you're going to see on exams are going to be similar to the ones that we're working in the in-class exercises and in lab, which is to say probability problems where you have to extract probability statements from the problem and figure out what's being asked and figure out what probability rules to apply in order to get that answer, not this kind of highly theoretical content that was the subject of this video. Okay.